In previous video, we have learned about the evaluation order, and we have seen how the evaluation order it affects the execution speed, and also related to the evaluation strategies we have seen. Based on the evaluation order, we can categorize the evaluation strategy also. Different types of languages like strict languages, non-strict languages, all these we have seen. And so lazy evaluation, it will be playing a vital role in the resulting in side effects. So its performance varies based on the side effects. So we are going to learn some new concept like streams and monads. The main purpose of this is usually the side effect will be found in the traditional IO, and these side effects will be due to the changes in the non-local variables or the variables that is shared between the functions, and also based on the inbuilt functions like read and display. So in scheme, there are two functions like read and display function, in which the read function will be each time when the read function is invoked, it will be reading some values, different values, and it will be returning those values to the display function, or those values will be taken by the display function so that it can be displayed. So what is the value that is read recently will be displayed on the screen also. So a side effect is there. Based on the value that is read, it will be displayed. So one way to avoid this side effect is to model the input and output in the form of streams. So different values is being read, and based on the values that is being read, it need to be displayed on the screen. So this can be modeled based on the streams or monads. So streams are unbounded length list whose elements are generated lazily. When it is required only, the elements will be generated. So how it is being implemented? It forces the evaluation of CAR of output, prints it and repeats the operation till it becomes empty. So here we are making use of the display function. So the driver, it will be taking one argument in the form of lambda expression, and that argument can be some list. Okay, so driver output, so some list, if it is taken, means taken in the form of output, it is taken, and for the display we are writing this function. Okay, so driver some list, if it is taken, means it will be given as an argument, that is yes, and from the S it checks whether the list is null or not. If it is null, okay. If it is not null, what it does, it takes the head element or the first element from the list using the construct CAR. Okay, then what driver, again it recursively calls, passing the parameter again some list, that is CDR of S. CDR S. CDR means removing the first element, the remaining part will be given as an input to the given as an argument to the driver function. And again it continues, it checks whether the list is empty, takes the head element, removes the head from the list, repeatedly it continues till the list becomes empty. In this way, all the values that is read via the input will be displayed on the screen one by one. So an interactive IO with the streams, an example like a square of number that is given in a sequence. So it is given like this. See, define the output, squares input. So square is a function that is defined. It will be taking an input as an argument. So input will be considered as some list of n numbers which is given in place, which is taken as S. And then what it does, it will be constructing a list where n is assigned as CAR S. S is the list, n numbers list From that n number list, it will be taking the head, that is the first element, store it in n, and checks whether the n is empty or not. If it is empty, it will be returning like that. If it is not empty, it constructs CONS using CONS. It constructs a list, takes the square of the number, and again constructs another list giving as an argument word squares of CDRS. Okay, so after removing the first element, the remaining elements will be given, and this square function will be called recursively. So this process will be continued till it reaches to the end of the list, which means n, when it becomes empty, it means that it reached to the end. So the result will be like n numbers that you have given, the square of those n numbers will be displayed, or will be stored as a new list. So this is a case how you can implement using the streams. Prompts, inputs and outputs would be interleaved naturally in time. Lazy evaluation would force things to happen in proper order. So what is given in the previous example, it is explained over here. Then the next concept is related to monads. Streams form the basis of I/O system in early versions of Haskell. Disadvantages of streams include doesn't work well for graphics or random access to files, and it is difficult to accommodate I/O of different kinds in streams. The solution is to use of monads. More recent versions of Haskell. So here we are making use of Haskell language. So Haskell employ a more general concept known as monads. They are drawn from a branch of mathematics known as category theory, and monads usually used in higher order functions, which allows the programmer to chain together a sequence of actions or function calls that have to happen in order. So there will be a sequence of actions which will be done in an order. Those actions will be treated as a function calls. So monads has the ability to carry a hidden structured value or arbitrary context from one action to the next. So this hidden structured value, these values, they are mutable. That is, it will be changing based on the actions that is carried out on those values. So an immutable object is an object whose state cannot be modified after it is created, whereas mutable object can be modified after it is created. So the hidden structured value which is given which is passed from one action to the next, those values, they are mutable objects. In most Haskell monads, hidden state can be explicitly extracted and examined. I/O monad is a type of monad meant for input-output tasks, where only part of its state is defined in library header file. The rest is implemented by the language runtime system. So a part of initially it will be defined in library header file. Only a part will be defined. Later monads will be updated or implemented using the language runtime system. So some of the functions that is used is map function. So map will be considered as a higher order function. As we have said, monads are used in higher order functions. Monads are also used in higher order function. That is map, one example. Then map function, what it does, it will be taking function f and a list L as argument. Function f and list L as argument, which will be returning a list that contains the result of applying f to the element of L. For example, here in this case map, it will be taking a function and a list of arguments. Okay, so here what is the result? It will be applying the function, that is here plus 7. It will be applied on the list of each elements. So it will be resulting in 8, 9, 10, 11, 12. That is summing each individual elements with 7. Then again, here, next one example, a map function. Using this map function, first line indicates the function initialization. This line indicates the function initialization, where this symbol, it indicates is of type, is of the type, and A gives B, defines a function that is from A to B, and here A indicates a list where the last, that is this entity, will be considered to be as the return type. Okay, it will be returning some other list. So map is of type function, function that is A to B, function from A to B, where A is a list of elements, and it will be returning some value B. Then another one map function. Here it denotes some empty list. It is F denoting some empty list. Then that is the base case. And map F, H colon T, it is used to take one element from the list. That is, one by one elements will be taken from the list, in which H will be the head of the list and T is the tail of the list. That is the remaining elements after removing this head. Okay, head will be one element and T will be the rest of the elements that is found in the list. And what it does, from the first element, it will be taking from the list and applies the function F on the list and concatenates them with the remaining list. Okay, it applies the function F on the first element of the list and concatenates it with the remaining elements of the list. So this is related to the map function. Then most basic output action is putchar of type IO, type char IO. Putchar is monadic function with an explicit character argument and no explicit return. So putstring is of type what? String. Putstring is putstr is of type string. That is a mapping to IO function. So this is the function initialization. So this indicates the function initialization of putstr. So here putchar is given and it is defined. It is given to define this putstr. So the result of map putchar, S is a list of actions, each of which prints a character. So sequence underscore map putcharas means that it will be printing a list of characters that is found in the list. Okay, character by character, elements will be elements that is stored in this S will be displayed or printed using this sequence of sequence underscore operation. Okay, sequence underscore prints a list in a single action. Putchar will be taking character by character from the list. The entry point of Haskell program is always a function main. It has a type IO, and because Haskell is non-strict, so Haskell is lazy or non-strict. The action sequence term returned by main remains hypothetical until the runtime system forces its evaluation. So how the main program will be given in Haskell is main is equal to interact my program. So interact here, micro program will be the name of the program, that is